Hi guys, welcome to chapter 41. Basically, this is built up on chapter 40. In chapter 40, we have seen Schrodinger's equation. If you guys remember, Schrodinger's equation was, let me get my drawing tool in here. And I will share with you the screen first. So again, we saw Schrodinger equation basically from chapter 40. I did not have it. Chapter 40 being negative h bar squared over 2m times the partial derivative with respect to x of the function psi plus the potential energy in general times the same function psi is equal to I h bar, the partial derivative with respect to time of the function psi. We made an assumption then in chapter 40, that is, that the function psi, which is assumed to be a function of both x and t, is somehow equals to the dependence on x times the exponential of negative I-E t over h bar. When I take the derivative of this function with respect to t, all I'm doing in this case is this doesn't depend on that. So this stays as is, doesn't depend on t, that is. So I'm going to drop a negative I-E over h bar and times the same exponential. That's properties of the derivative of the exponential. Well, if I do that, then I will have this term on the second half, and I will have it also on the first half, and I will have it also on the first half. Notice that this one times, if I multiply it by this factor, which is I h bar, well, the I h bar and the h bar cancel, and the negative I times I from this term is going to simply be plus 1. So this equation can be written without the time dependence as basically equal to negative h bar squared over 2m times the second derivative of the function little psi with respect to x plus u with respect to u sub x times the little function psi is equal to e psi. We dub this one, or we call this one, as the time independent Schrodinger equation. So this is the time independent Schrodinger equation. And this one is the full-fledged Schrodinger equation that we worked in. Okay. The difference in this situation is that this term now depends on x. Let me explain what these terms mean. I mean, if I take psi as a common factor from this expression, times psi. I know you're expecting what kind of multiplication is this? This is called an operation, not a multiplication. So this becomes an operator. So what does this operator do? It multiplies u by psi, and it takes its second derivative from this term. So that's all. So this is an operator, and this is equal to e psi. So this operator looks like it's some sort of an energy because this part is the potential energy of it. So this looks like it's the kinetic energy part of it because the whole thing is the total energy of the system. Okay, and this formulation actually of this equation in here, Schrodinger's equation, is actually an expression of the energy. That's all. This is an expression of the energy where there is a correspondence between the position. So every time we found u, when we found x, we left it intact. So when we were writing u sub x, we left everything intact. So x, when you see it, leave it as is. So this is the classical x. And this is the quantum mechanical x. Okay, the position. The momentum, though, and let me explain what I mean by that. This looks like it's a kinetic energy. But the kinetic energy in this situation is of the form, it's of the form negative h bar squared, the second derivative with respect to x, okay, divided by 2m. This should correspond to p squared over 2m. Remember that the kinetic energy term is equal to 1/2 of mv squared, in classical mechanics, of course, where mv is the the momentum P. So if I square this quantity and plug it into the expression, I'll get P squared over 2m. So this looks like it's P squared over 2m. So whenever I find the classical momentum P in this situation, I have to replace it by, because the 2m is the same, so I'm not too worried about that. So I have the negative, which should operate as an I when I take its square root, because this has a P squared in it. So I have to take its square root times H bar times the partial derivative with respect to x, because I'm taking it in here in the sense that I'm doing the independent Schrodinger equation, but in general, it doesn't have to be that. I mean, the function psi itself, and we're going to see it shortly, could depend on x, y, and z. So if I'm doing it for the y position, for example, I'm going to leave the y the same, but the momentum, so this is the momentum in the x direction. The momentum in the y direction should also look like this term. Okay, and the same thing, the momentum and the position in the z direction should give me a similar term. So this is how I go from classical system to a, now I write this side using these operations. So normally the kinetic energy in general is the entire momentum divided by 2m, where momentum P is a vector of components px, py, pz. So its square then is normally px squared plus py squared plus pz squared. So again, I know we didn't really build this theory, and I hope that you guys did not believe that I proved the Schrodinger equation, because last time we went through an argument that connects the angular frequency with the wave number, and we said that the requirement for omega to be proportional to k squared, in that case, some sort of dispersion law, and we argued that the Schrodinger equation should look like that, and then we generalized the idea without proof that we add to it u. Well, in this situation, Schrodinger's equation really should be assumed as some sort of a postulate. So first of all, the wave behavior is defined by function psi, whatever that psi turned out to be, because it turns out to be a complex number, which is very hard to explain. So the assumption is that there is a psi that justifies that. That's one thing. The other thing also, it has to satisfy Schrodinger equation. Once we find psi, usually it's amplitude square, I mean by the whole psi, not necessarily this one. Once that, the whole amplitude has a meaning. The square of the amplitude, as a matter of fact, is what we call the density probability, meaning what are the likelihood of finding a particle in a specific location. And I know I did not talk a lot about the measurement. So when we do a measurement, and I think we talked about it in talk when we were referring to the lab, when we do a measurement about a certain quantity, it doesn't matter what that quantity I want to measure, and I want to find its average. So this is just an average, okay? So if I want to do an experiment, this is probably what I'm going to have. I'm going to deal with a bunch of particles. So it's going to be in this situation, the sum from negative infinity to positive infinity for where the particles could be. I'm still dealing with the 1D so that you guys understand, so that this integration is over dx times, in this case, because this side could be potentially a complex number, so it's times the complex conjugate of this function times the quantity that I want to measure times psi itself, okay? This operation better be in this order. Why? Because this quantity that I want to measure could have in it P, either one of these P's. I mean, I still probably do, so it still have this P potentially. And the derivation, it's not true that, for example, if I take the function x times the derivative with respect to x and operated on the function psi, for example, is the same thing as the operator of the function x when I multiply x times psi. In other words, if I take the derivative first of psi and multiply it by x, I will just get x times the d psi with respect to x. However, if I multiply first by x and then take the derivative, it's clearly not going to be the same thing, because the derivative of x times psi is first this term, namely the derivative of x with respect to x, which is 1 times psi, plus, in this situation, x times the derivative of psi with respect to x. So in other words, the order matters, because this quantity has a potential to becoming this derivative if there is a momentum involved in it. So this is basically the measurement. I'm assuming that the function is normalized, meaning that the sum of all psi squared dx from negative infinity to positive infinity is equal to 1. So this is the normalization condition. Again, this is just some sort of a review from before and basically trying to tie the things up a little. But then this is what we do when we actually do a measurement in the laboratory. We take this quantity in here. Okay. Here is, we want to take this equation and write it now in 3D. So what I'm going to do again, I just argued that the momentum then in this case is the sum of these three quantities, because momentum is a vector that has components in the x direction, y direction, z direction. So the kinetic energy then should have a negative, because I'm going to square that quantity, negative h bar squared over 2m times the sum of the momenta, which is the derivative with respect to x, times the function psi, or operating on the function psi, plus the derivative with respect to y now, plus the derivative with respect to z. So this is generalization to the problem that we did, plus a potential which may depend on x and y and z, times the function is equal to, in this situation, I h bar, the derivative of the function psi with respect to t. Okay. The function psi is a little bit complicated in this situation. It's typically, as I was saying, function of x, y, and z in t. So we took it from 1D to 3D. So this is 3D Schrodinger equation. And as a matter of fact, we're going to do the same thing as before and write it as a function that depends on the spatial parameters times the exponential of a negative I e t over h bar. In other words, this derivative on the second half is just going to be et, and then we get e every times psi, and then at the end we're going to get rid of that temporal behavior. So the equation of Schrodinger equation becomes simply an equation in space. So it's going to be minus h bar over 2m times the derivative with respect to x squared plus the derivative with respect to y plus the derivative with respect, all of this are second order derivatives of the function psi, plus u now, u doesn't depend on t, u depends on x, y, and z, at least for the problems we deal with in quantum mechanics, okay? Times the same function psi is equal to e psi, okay? I already got rid of that exponential on both sides, because when I take the derivative, I drop a negative IE over h bar, and the h bar cancels that h bar, and then negative I times I becomes 1, because I squared is negative 1 times negative is going to be a positive 1. And then you drop the E, of course, and here is the E. So again, this looks like the total energy is some sort of a potential energy plus kinetic energy exactly from this principle that I've used. You have to understand in this book, at this level, we're using Schrodinger equation. There is another formulation for quantum mechanics, which we're not going to get into, where the temporal behavior is not carried by the function psi itself, by the wave function. It's carried by what is known as operators, and I already alluded to them in this expression here. And this whole thing becomes what is known as the Hamiltonian operator, okay, without the psi in it, okay? So this is, if you're gonna get into advanced courses in quantum mechanics, you will see that notation a lot, because it makes life a little easier. And the temporal behavior is not expressed in terms of this ones. You will see that some problems at least will become a lot easier to deal with in that approach. In the early on, the theory of quantum mechanics, when it came about, there were two competing schools of thought, the Schrodinger equation, one on one side, arguing that this is the only way to do things, and Heisenberg's formulation, which was completely different in saying that this is the only way to do things. And at the end, both of them are similar, actually, and they lead to the same result. Anyway, so this is Schrodinger equation that we will be dealing with in this chapter. So it's in 3D. So the first problem that we're going to tackle is our old problem, a particle in a box. And this time around, we really mean a box of size L. So imagine you have a cube of width depth L, capital L. I'm not gonna write it as side L and height L. Okay. So the volume is clearly equal to L cubed. Very simple. So we want to find a solution for a particle that is in this box, but we're going to add to it the condition that this particle is free. As long as it's inside the box, it's free. Meaning u equal to 0. That's what the free means. U is equal to 0 here. So the equation, Schrodinger's equation, then will drop the second term in it. So this term is 0. So the only terms we have to worry about is this dependence on x, y, and z of the free particle as long as it's inside. We expect outside when x is greater than, in absolute value, I'm going to take it, greater than L, or y is greater than L. What am I talking about in here? Sorry, I took it from 0 to L. So x is greater than L or x less than 0. Let me put it this way. Y is greater than L or y is less than 0. Z is greater than L or less than 0. If any of this happen, psi is equal to 0. Meaning the particle doesn't exist outside. So I'm taking some sort of a coordinate system in here. It's probably starting from here, where this is my x-axis, goes from 0 to L, x, y, and z. So this is my y-axis, and it goes from 0 to L also, and the z-axis in this case is going to be from 0 to L. Do I have it right in here? X, Y, and Z, yes, correct. Okay, it has to be a right hand. So this is where the particle is trapped. Anything outside of this box, the function psi itself is 0. So the particle cannot exist outside of the box. This is important because we're going to impose our boundary conditions on our particle and force it to be in this box. So again, let's write this equation and see how it looks like now. So it's going to look like minus h bar squared over 2m times the second derivative of psi with respect to x minus h bar squared over 2m, the second derivative with respect to y of the function psi minus h bar squared over 2m times the second derivative of psi with respect to z is simply e psi. Here is what I'm going to do. I'm going to usually use the method of separation of variables, second derivative with respect to z. So I'm going to use the separation of variables. This is a common method used when you deal with partial differential equations. So what I'm going to say in this case, the function psi, which is typically a function of x and y and z, is can we have a solution so that its x dependence is only carried by the function x. Its y dependence is carried by the function y. Its z dependence is carried by the function z. Okay? So if that's the case, obviously the second derivative of psi with respect to x is going to involve only the function x. So it's going to be the straight out derivative of x with respect to x times yz. And similarly for the other two, namely the second derivative of psi with respect to y is equal to the second derivative of y with respect to y times xz. And finally, the second derivative with respect to z is simply equal to the second derivative of z. I'm sorry, it has to be straight derivative, not a, because there is only one dependence on z. So the second derivative of z with respect to z times xy. So we sub into this equation everything, and we see what we get. So the first term in here is going to be the second derivative with respect to x times yz. So I'm going to have minus h bar squared over 2m times yz times the second derivative of x, actually, with respect to x. The same thing with the second term, minus h bar squared over 2m, but I will have an xz times the second derivative of y with respect to y. And the last term in here is minus h bar squared over 2m times xy, the second derivative of z with respect to z is equal to e times x times y times z. I'm going to divide both sides by x times y times z. So I'm going to divide both terms by 1 over, or multiplied by 1 over x, y, z. Obviously, y times z from the first term in here, cancel this y and z. This y and z in here, oops. This y and z cancel this y and z, and it would be left with an x in the denominator. This x and z cancel this z and x, and it will be left with a y in the second term, and so on and so forth. Well, the second side will have nothing except the e in it. So I'm going to write the second side in here as e in it. And the first side is going to have minus h bar squared over 2m times 1 over x, the second derivative of x with respect to z, minus h bar squared over 2m times 1 over y times the second derivative of y with respect to y, and minus h bar squared over 2m times 1 over z times the second derivative of z with respect to z. Obviously, the big Z is the function, and the little z is the independent variable. Okay. This side is constant. There's no x, no y, no z in it, and I mean the variables. This term should depend only on z. This term should only depend on y, and this term should only depend on x. One way for them to do that, if this term does not have anything in it in x or y or z, and the same thing for the other two. So what I could say in here is I could impose the following condition, that E, the total energy, must be a contribution, because this is a free particle, so the only thing that is coming is the kinetic energy. So there is a contribution to the kinetic energy from the motion in the x-axis. So I'm going to write it as E of x. I don't mean that e to the power x or e is some sort of a vector. No, it's just a contribution to the total energy of the system coming from the motion along the x-axis direction. Same thing. The second term, I'm going to call it the contribution to the energy from the motion along the y direction. And the third term is E of z, meaning that what I'm talking about in here is the contribution of the motion along the z direction to the total energy, so that the total energy really is the sum of all of these three contributions. So that's how am I writing it. The thing with it is, at this point, I don't know what Ex is or Ey is or Ez is, but this is what the equation is telling me. So what this equation satisfies in each and every one of them is, so this term is equal to Ex, this term is equal to Ey, and this term is equal to Ez. Obviously, this means that minus h bar over 2m times the second derivative of x with respect to x is equal to E times x. I took the x in here and I multiplied by both sides. The same thing with the other, so E sub x in here. The second term in here is minus h bar squared over 2m times the second derivative of y with respect to y is equal to, again, E in the y direction, or the contribution of the y direction, times y. And the last term in here is minus h bar squared over 2m times the second derivative of z with respect to z is equal to E, as it's added, I'm sorry, from the z direction, times z. Again, I had 1 over z in here, and that 1 over z I multiplied by it. That's how I ended up with it on this side. Each and every one of these equations look awfully similar to that of the harmonic oscillator that we did in physics 1. If you guys remember in physics 1, we said that the acceleration, which is the second derivative of the position with respect to time, is equal to minus k over m where I divided by m, the mass, and this is the spring constant times x, and we said that the solution of this equation in general is some sort of a cosine of omega t, and omega is just the square root of k over m times t plus another contribution coming from the sine over k over m, where in this situation a and b were determined by the initial conditions, and in this situation I have the boundary conditions that I wrote them up there. This ones that I need to impose on my function. So let's focus on one direction at a time. Let's look at the x direction. For the x direction, and we're going to write for the other directions right away. So for the x direction, I have this equation, and this equation then suggests that x as a function of x then is equal to a times a cosine of the square root of 2e times m, 2me divided by h bar squared. So it's 2me in the x direction divided by h bar squared times x, and plus b times the sine of the square root of 2me in the x direction divided by h bar squared, the whole thing times x. And the boundary condition is if x exceeds L or x is less than 0, the function psi itself equal to 0. That means the contribution from the x direction is 0. So what that means is x of 0 is 0, and x of L is 0. To satisfy the boundary conditions, when the particle hits the boundaries, the function must vanish. Okay. So again, if I plug in x equals to 0, the cosine of 0 is 1. So a times 1 plus b times sine of 0, which is 0, must be equal to 0 according to this condition. Well, b is equal to times 0 is 0, but a times 1 is 0. That means a is equal to 1. So there is no cosine term in here because of the fact that a must be equal to 0. The second condition now says that this b times sine of this whole thing times L equal to 0. So what that means is that b times sine of square root of 2m, the contribution from the x direction into the energy divided by h bar squared times L must be equal to 0. I cannot have b equal to 0 now, because if I have b equal to 0, that means x equal to 0, and the particle doesn't exist inside either, because of the fact that this is the behavior of how it looks like inside. This is x is equal to 0. Remember, psi is x times y times z. Big X times big Y times big Z. So big X is equal to 0, we're done for. We don't want that. So B cannot be equal to 0. That is, otherwise we will have a trivial solution that is not acceptable. So the only thing in here is that this sign must be equal to 0. And if the sign equal to 0, that means its argument is multiples of pi. It could be 0, it could be pi, it could be 2 pi, or 0, negative pi, negative 2 pi, and so on and so forth. So that means that 2m ex over h bar squared under the square root times L must be multiples of pi. Since I have the same equation in the y direction, here it is, in the z direction, and I'm trying to focus on each direction at a time, so I'm going to call this integer n of x. So where nx can be anything if you wish, except 0, honestly, because if it's 0, then the sign of 0 is going to be back to 0, and we don't want that. So nx really should be plus or minus 1, plus or minus 2, and so on and so forth. Okay. As a matter of fact, we're going to focus only on the plus signs because of the fact that we're going to recover the others just by symmetry in this situation, because all we really need is a sine squared, namely the amplitude of these functions. Okay. At the end of the day, the solution then, x of x, looks like this. X of x is some constant, which I'm going to call it, let's call it b sub x also, because remember, we might have another component from the y direction, another one from the z direction, and so on and so forth. So times the sine of this whole thing, the square root itself, is this term in here, divided by L. In other words, this square root of 2me sub x divided by h bar squared is nothing but this nx pi over L. So this becomes nx pi x over L. That's it. This looks familiar because it looks like the particle that we did a long time ago. So now, here is the thing. For the y direction, it's going to be identical, except replace x by y. So it's going to be a sine, because the conditions are identical. And another integer we're going to pick up, y over L. And the same thing is true for z sub z. And that too is some sort of a constant. And these three constants, when we multiply them, become just another constant, okay? So bz times another sine of nz now, times pi times z over L. Okay, where each and every one of these contributions to the energy is related to these integers that we just introduced. And square root of 2me in the z direction contribution to the total energy divided by h bar squared is related to, I'm sorry, this is ny. Why am I writing it nz? Again, nz in this situation, pi over L. Okay, so this is the solution. The solution itself actually will have a constant. So the solution, remember, is x times y times z, is just another constant, where b is just the product of the other constants, because it's a constant, and it's going to be determined by the normalization condition anyway. Sine of nx pi x over L times sine of ny px over L times the sine of nz pi, I'm sorry, yx, this is y, and this becomes z over L. Okay, so we have all of our wave functions, and the condition, the constant b is determined by normalization condition. Let me take these square roots and multiply them, because we need ex, we need ey, we need ez, and we need to add them together, if you guys remember, to find the total energy. So we really need to find the total energy also. And from the first equation, we can find ex just equal to nx squared pi squared over L squared. In the numerator, we will have h bar squared and divided by 2m. So ex from the first equation depends on that index n. So it's going to be in nx squared times, because you have to square both sides, times pi squared h bar squared divided by 2m times L squared. Okay, and the same thing is true for the other variables. So ney is going to be the same thing, ny squared, where these n's are all integers, 1, 2, and so on and so forth, pi squared over 2ml squared. And finally, ez is going to be nz squared times pi squared h bar squared over 2ml squared. Okay. The total energy is the sum of all of these three quantities, as I was saying earlier. This is where we started from. So E is just add all of these three numbers since they have the common factor. So E must be nx squared plus ny squared plus nz squared. And the whole thing is multiplying pi squared h bar squared over 2ml squared. Okay, it's worth remembering that 4 pi squared times h bar squared is nothing but h squared. So in other words, 4 pi squared h bar squared is nothing but h squared. So we could replace this formula writing it as h squared over 8ml squared, because you will have 4, times 2. That makes it 8. So these are the energies of the system, and they are actually depend on these parameters nx and ny and z. So I have enx, eny, enz. So basically, it depends on all of these three integers, this energy. So it's quantized, and its quantization depends on 3 quantum numbers, not just 1. Okay, because it's 3-dimensional problem, so we have 3 quantum numbers, and 3 quantum numbers are nx, ny, and nz, and each and every one of them can be anywhere from, no 0, 1, 2, 3, and so on and so forth. Okay, and the wave functions themselves I mean, if you're worried about the negatives you just change the sign in here and they can be absorbed in the normalization definition of your function, okay? So it's no big deal. So the condition of the normalization again is that psi squared integrated from negative infinity to positive infinity through the entire volume in this situation with respect to x, with respect to y, with respect to z, integrated. In this situation, we're bounded from 0 to L for all of these three variables. This must be equal to 1. So if I do that, that means I have a b squared times sine squared times sine squared times sine squared integrated over dx, dy, dz is equal to 1. So in other words, I have b squared that shouldn't depend on anything. It's a constant. The integration from 0 to L of dx times basically this term, sine squared times sine squared of nx pi x over L times, I'm going to separate the integrations and make them all one-dimensional integrations because these parameters, they don't depend on each other. So sine squared of nx again, ny in here in this case, pi y over L square, there is no square, the sine squared itself takes care of that, times, I don't have space in here, so this times, not x times, 0 to L of dz times sine squared of nz pi z over L, the whole thing must be equal to 1. Obviously, this term in here, if I do the change of variable and move things around, namely with a dummy variable, call it x prime if you wish, so that it's nx pi over L, and the integration from 0 to L, well, when x is equal to 0, x prime becomes equal to 0, but when x equal to L, the integration from 0 to 1 and to n pi, okay, n pi x, and this will pull for me 1/2 times the, don't forget I will pick up a new term in here, which is going to be L over n pi x, and that n pi x cancels the n pi x, so it's going to be L over 2 basically, and I will have an L over 2 from here and an L over 2 in here, so it's going to be L cubed over 8. So the b squared should be, please verify this one in here, L cubed over 8 is equal to 1. From here, I have b, which is typically taken to be real, as 8 over L cubed, under the square root, of course, okay? Where L cubed is going to be our volume. Anyway, the point being in here is that we have found the normalization, we can find the normalization condition. We have found our wave function. Don't forget that this is not the full wave function. You still have that exponential with respect to time, namely negative I et over h bar. And that should give you the full-fledged function, okay? So if there is a superimposition, so these are the modes. These are called actually the different, and this psi also depends on nx, ny, and nz, these three quantum numbers, and you can clearly see from that. Here is what is interesting in here. And this only happened in 3D. We cannot see it in 1D, okay? Here is the thing. The lowest state, of course, corresponds to nx equals to ny equals to nz equals to 1. Because all of them, they start from 1. And if that's the case, the energy then becomes energy of 1, 1, 1, this state. Remember, E1, 1, 1 is just 1 squared plus 1 squared plus 1 squared, which is 3, times pi squared over h bar squared over 2ml squared. So this becomes simply 3 pi squared h bar squared over 2ml squared. So this is the lowest energy level. And this corresponds to the function psi 1, 1, which is equal to that constant b, which is square root of 8 over L cubed, or volume, times sine, in this case, n is 1, pi x over L, sine pi y over z, pi y over L, I'm sorry, sine pi z over L. So that is one ground state with one energy. Here is where it becomes important. Now, here is where it becomes kind of different. If I choose nx equals to 2, but keep ny equals to nz equals to 1, or choose nx, ny is equal to 2, and nx is equal to nz is equal to 1, or choose nz equal to 2, and nx is equal to ny is equal to 1. All of this will correspond to the energy level, which I'm going to write it as E211, which is going to be the same thing as E121 or E112, which are going to be the same thing because there is a perfect symmetry in this problem in here for the energy. All I have to do is either add 2 squared plus 1 squared plus 1 squared, which is 6, or 1 squared plus 2 squared plus 1 squared, which is 6, or 1 squared plus 1 squared plus 2 squared, which is still 6. So all of this will give me 6 times the same factor, 6 times pi squared h bar squared over 2ml squared. And this simply equal to twice this number because this is 3, this is 6. So this is just twice as much as we had in the lowest energy level. So these states are clearly different than one another because each and every one of them will correspond to a different wave function. Let me write these wave functions in here. So the first one is psi 211, and that is equal to square root of 8 over v times sine of 2 pi x over L times sine of pi y over L sine of pi z over L, and this is clearly not the same thing as sine 121, which is square root over 8 over v times sine of pi x over L sine of 2 pi y over L sine of pi z over L. And this one is not the same as sine 112, which is square root of 8 over v sine of pi x over L sine of pi y over L times sine of 2 pi z over L. So all of these three different wave functions are completely different. They depend on the variables in a different fashion. So they cannot be the same. But they all have the same energy, which is twice as much as we have this one in here. So this is called the degeneracy. Degeneracy. Okay. In other words, the energy level, this energy level is degenerate. You have different ways of having the same level. And this is because of the fact that we have really a symmetry. Let me explain what I mean by that. If I take my original cube and spin it around the y-axis, the z-axis becomes in the place of. So if I spin it this way, then the z-axis replaces the x-axis, and the x-axis replaces the negative z-axis. So in that case, the same problem becomes similar. Or if I take the whole thing and spin it around the z-axis, then in this case, the x-axis replaces the y-axis, and the y-axis replaces the negative x-axis. Okay, so there is a perfect symmetry in this situation. It has to do with the rotations, and that's why I have degeneracy in this situation. How can I fix the degeneracy? If I take these L's and make them not the same, then obviously these contributions to the energies, they will have one L in here that is not the same L in here, that is not the same L in here. So in other words, Lx, you have an Ly, and you have an Lz. If that's the case, then when I sum up these numbers in here with a 2 in front of it and a 1 and a 1 is not the same as when I sum 1 times 2 because the denominator is not the same. But because this factor is the same in the energy, right now we have degeneracy. So one way to fix the degeneracy and leave it is by breaking the symmetry. Because we have symmetry, it really leads to this one. So in order for me not to have degeneracy, I can break the symmetry. And this important is going to be important later on. So if we have a system that is like the hydrogen atom, for example, it's perfectly symmetrical, we assume that the potential in this case depends only on R. So in this case, we have some sort of a spherical symmetry. But if I take the whole particle, for example, and place the magnetic field, then in this situation, I broke down the symmetry because there is a direction for the magnetic field where the electron, as it's spinning around the nucleus, then in this case will interact with the magnetic field, and the degeneracy should be broken then. So that's in a similar sense. So this is the particle actually there is more than this. I mean, I can go to the next energy level, which will take me 2 to 1. So in this situation, I will have 2 squared plus 2 squared, that's 8, plus 1, that's 9. 9 is going to be 3 times E11. And then, so this is how the energy levels look like. So then we have the ground state. And then we have the next energy level, which is E211, and this is degenerate into 3 wave functions. And then you have E221, and then you have before you get into T222, which is going to be what, 412 divided by, so it's going to be 4 times. There is another level actually in here, E311. And E311 will be 9 plus 1 plus 1, so it's going to be 11. So it's going to be slightly more than E221, but less than E222. So it's going to be just below E222. So these are the energy levels, and they are not the same. They are not all uniformly spaced. Actually, this distance is the same as this distance, but this distance is not the same, and this distance is not the same as well. Okay, so the energy levels are going to be, some of them are going to be degenerate, and that is speaking about the symmetry that you have in problems. So whenever you see degeneracy, you typically talk about symmetry in the problem. And one way to remove the degeneracy is to make sure that the system is not symmetrical anymore by presenting some sort of constraints on it. Okay. Before I finish this recording for you guys, let me start the problem for the hydrogen atom, since I mentioned it. So the hydrogen atom, which is the simplest of them all, you have 1 proton and 1 electron. I mean, you could have a proton and neutron, so you could have the heavy atom, the heavy hydrogen, but that's deuterium, that is. But for right now, you have positive charge inside and negative charge orbiting it. Okay, so this is the problem that we're facing. Obviously, the potential in this case, U, depends on R only. And if you guys remember from your class from electricity, it's equal to minus E squared over 4 pi epsilon naught times R. Is it a minus or plus? It's going to be plus, because the force is a minus and the force has a gradient in it, and the gradient will ensure, no, it's a minus, because there are 3 minuses, I'm sorry. There is a minus of the gradient, the definition. There is the minus that is coming from the definition, from taking the antiderivative of 1 over R squared. And there is the minus that is coming from the charges, because these are attractive forces. So this should be a minus in here. Okay, so that is one thing, okay, for the potential energy. So the potential energy depends on R, and the problem has to be, we cannot really write Schrodinger's equation in this situation. Of course, we're going to write the whole Schrodinger equation now. The time-independent version of it, namely this equation, not this one. This is the time-independent one. I mean, this is the time-independent still. Both of them are going to use the time, but this had a potential 0 for a particle in a box. Now we're not going to take a particle. We're going to take this whole thing, but instead of, because U depends on R, so we really are better off to use spherical coordinates. Spherical coordinates. So what are spherical coordinates instead of Cartesian coordinates? If you remember from our math class, basically a particle on a sphere is, at least in spherical coordinates, is determined by the radius R. And So this would be the z-axis normally. So this is the z-axis, and this is x, y, and z. So let me redraw it because I drew it. Okay, so this is the x-axis, x, y, and z. So this would be my y-axis, and this would be my z-axis. I think this is better. So this is x, y, and z. So we have particle in space. It's in here. It has components in the x direction, expressed as x. So this is r. This angle is theta. This angle varies from 0 to pi. Okay. And obviously from here, you can clearly see that the projection in the z direction is the adjacent to r. So in this case, z coordinate is just r cosine theta. And the projection of this point on the plane xy will give me x times sine theta, which is this component, but I will have an angle now phi with respect to the x-axis. So we're going to use r theta phi in such a way that the x coordinate is really equal to r sine theta cosine of phi, and y is equal to r sine of theta sine of phi. We need to take that kinetic energy term, which is really p squared over 2m, which is really px squared over 2m squared 2m plus py squared over 2m plus pz squared over 2m, and write this term in terms of spherical coordinates. The derivation is very long, okay, because this is what you get to do. You have to, first of all, write r squared, which is just the sum of all of these terms in here, as just being x squared plus y squared plus z squared. I mean, it's very easy to straightforward show that because of the fact that you have to take the derivatives and so on and so forth. Then you have to take theta. Theta is clearly, if I take x squared plus y squared under the square root, the cosine squared and sine squared add up to 1, and you will have an r sine theta divided by r cosine theta. When you divide it by z, you're going to get tangent of theta. So tan of theta is going to be square root of x squared plus y squared divided by z. And finally, if you take if you take y over x, you're going to get tangent phi. So this is the reverse, if you wish, transformations to go from Cartesian coordinates to polar coordinates, namely r, theta, and phi. So this was going to be y over x, I'm sorry. So what you got to do in this case is rewrite these terms, namely the second derivative with respect to x, in terms of all the combinations. So first of all, you write d sub x, the first derivative, which is going to be dr with respect to x times d with respect to r plus d theta with respect to x times the derivative with respect to theta plus d phi with respect to x times d with respect to phi. So now what you have done in actuality, you took the derivation that was in this form px squared. Remember the transformation that I had before? I had the kinetic energy equal to the second derivative with respect to x, namely this term, minus h bar over 2m, so I'm not worried about that constant, times the second derivative with respect to x. But before I get to the second derivative, I really need to get the first derivative term. So I will get one value in here, okay? I'm just showing you how you're doing it because we're not going to do this one. It's very, very long. I mean, I showed you how to do it for the case of polar coordinates, and that was long. And I shared with you the PDF file, and that was long. And actually, we probably are going to use that. Okay, so this dr with respect to x is straight out from this expression because you can clearly see, take the derivative of both sides with respect to x. On the left-hand side, you're going to get 2r times the derivative of r with respect to x. And the other side, you only have x squared in here to worry about because the other two are constants. So it's going to be 2x. So the dr with respect to x is simply equal to x over r. And x over r from this expression is equal to sine theta cosine phi. So you have a term in here which is sine theta cosine phi. And the same thing, d theta with respect to x, you're going to take this expression and take its derivative. D theta with respect to x. First of all, you take the derivative of the tangent, which is 1 over cos squared of theta, times the derivative of theta with respect to x. And this equals to, clearly you will have the square root, you bring up 1/2, and then square root becomes x squared plus y squared to the power 1/2 becomes x squared plus y squared to the negative 1/2. So it's going to be in the denominator. But don't forget, you have to take the derivative of the inside, which will give you 2x. So the 2 cancel the 1/2. So we're going to be with x, I'm sorry, with no 2 anymore. X divided by, namely, z times the square root of x squared plus y squared. Okay, x itself. So I will have 1 over cos squared theta d theta with respect to x is going to be x itself. I have it somewhere in here. I have it r sine theta cosine phi, r sine theta cosine phi divided by z, and z is r cosine theta. So it's going to be r cosine theta. And the square root of x squared plus y squared is just r times sine theta, r sine theta. Obviously, the r sine theta and the r sine theta cancel. And one of this cosine theta and cosine squared theta cancel. So at the end of the day, d theta, namely the second term in here, in this expression, d theta with respect to x is going to be simply equal to cos theta, cos phi, over r. Everything else is gone. Now, the last term you will need is, of course, d theta with d phi with respect to x, and that is coming from the last expression. Again, the derivative of the tangent is 1 over cos squared, but in this case, phi, 1 over cos squared of phi times the derivative of phi with respect to x, and this is what I am doing, what we need in here, is equal to minus y over x squared, because x is in the denominator in here, minus y over x squared. And again, y itself is just, so we have a minus r times sine theta sine phi over x squared, which is r squared, sine squared theta, cosine squared phi. I have a cosine squared phi and I have a cosine squared phi that cancel. I have an r sine theta that cancels with an r and sine theta, one of those terms. So at the end of the day, d phi over dx would be simply equal to minus sine phi over r sine theta. Okay, you do the same for the other two terms because this is just the derivative with respect to x. We still have to do the derivative with respect to y. In the same fashion, it's going to give me dr with respect to y, d with respect to r, plus d theta with respect to y, and d with respect to theta, and then finally d phi with respect to y, and the derivative with respect to phi. We're going to do the same steps in here with respect to x, so we'll have 2y in this case divided by r. As a matter of fact, it's going to be y over r. So this term is going to be sine theta sine phi, and this term will have a corresponding formula in here, and this term will have a corresponding formula, and you do the same thing for dy with respect to z. Okay? Once you do that, you're going to take the derivative of the derivative because you actually need the second order terms, okay? So to save you from the headache of doing all of this, and I'm sure you did this somewhere in one of your calc classes, I'm going to give you the results because it's too long, really. I mean, to do the whole thing. Okay, I wrote it up there, all the way to the top. And here is how Schrodinger's equation would look like. Okay. It's not exactly how it looks like because it's really going to have a sine theta and r and phi everywhere, not just theta and r and phi everywhere. So you do the same thing. You do a separation of variables in a similar fashion, okay, where the dependence on r is carried by the function r. So r in this case depends only on r. So this is the real part of the function itself, of the wave function. Theta itself, and I'm trying to write it as capital theta in this case, depends only on theta itself. okay? And capital phi in this case depends only on phi itself, okay? So in this case, you do separation of variables and you end up with these three equations. The last one is the easiest one to solve. As a matter of fact, that gives me a solution that look like this. Phi is similar in a sense, so there is a constant in here, which we don't care about, to I ml, because this is a positive number, so it's going to be ml, which is a number, by the way. Ml is just a number at this point, times phi, okay? So this is going to be the phi dependence on the wave function, okay? So this is important at this point. I'm going to end up with this discussion in here, this video, because it's getting very long, and we're going to finish the discussion to pick it up for theta and phi. Okay, we're not going to solve this equation in this case. It really requires more advanced calculus, and this is called actually this part, this breaking of the function itself in here. This is the Legendrian function and the Legendrian operator. And this is really, and the whole thing that we've been dealing with is called Laplace operator, by the way. And the whole thing is called Laplacian. This is a Legendrian, and the solutions for it are really Legendre functions, and becomes a little bit more advanced mathematics than what we have in our hands. But I'm going to give you the solution, at least. We're not going to give you the whole thing, but I'm just going to give you a feel for what this number in here means, okay? So e to the I ml phi. This tells me how the wave function depends on phi. In other words, it's periodic with respect to phi, that's all. And this periodic function better be under the following condition, meaning that the electron, as it orbits the nucleus, as it comes back after a full cycle, it must come back to the same value, because the wave function must be single valued. As a matter of fact, we can understand it by particle in a ring. Particle in a ring is that it's forced to be on a ring, okay? So it's oscillating, it's going, not oscillating, it's orbiting this ring. It's orbiting this point on a ring. So in this case, it's going to be somewhere in here where phi is some value, and as it comes back, it's going to be, after 2 pi, it's going to be e to the ml, the number that we input with the index L, times phi plus pi. I'm sorry, plus 2 pi. Okay, after a full 2 pi in this situation here. Okay, so what happened in this case? The wave function should not be different than what it was before, because its amplitude has a one unique definition, namely the probability density of the function and the probability density of the wave function. And if we do a measurement at this point, it doesn't matter what phase we are in, we should find the same value. So the function psi squared must be a single valued function. Otherwise, we really don't have a function. So when it has two values in the same location. So when we do an experiment, when we do a measurement, we really have to find only one probability, one value that corresponds to that probability density value, basically. So we cannot find two different values in this case. So what that means is ml times 2 pi must be an integer in this case. So in other words, must be in multiples of 2 pi. So in other words, ml itself must be an integer. 0, plus or minus 1, plus or minus 2, and so on and so forth. 0 is acceptable in this situation, because it's under the exponential. An exponential of 0 is just 1. Meaning that the function doesn't depend on phi at all. So the particle can be anywhere on that ring. Okay. And but if it's any other number, then it's not 0. It depends on phi then. Okay. A cosine phi or sine phi or something like that. So in order for the function to be single valued, this ml in here must be an integer number. So that is one thing. The other thing in here is ml cannot really exceed the value of L because of this previous equation. Because of the first equation, it really should not be more than L. In other words, because of this condition in here, in this equation in here. In the equation for theta, put a constraint on m, namely ml is an integer that varies from here up to plus or minus L. It cannot exceed that, okay? The last condition is the first equation. So this is because you have that sine theta in the denominator, and sine theta better be finite, okay? At theta equals to 0 or pi, okay? So that's why you have it in here. So you make that condition, and this is why you end up with ML less than or equal to L at most in magnitude. I mean, it could be plus L or minus L. The last condition is actually on this equation in here that will impose a condition on L actually itself. And that condition is L can be anywhere from L equals to 0 all the way to N minus 1. And N is the energy levels that you will end up with. And that is coming from these polynomials actually in here that develop from this expression. So at the end of the day, this is basically what you end up with. N is an integer number, can be 1, 2, and so on and so forth. That is the value for the principal quantum number call. And this is what Mr. Bohr has found. Okay, and this corresponds exactly to the same energy levels, to the same radii and everything else. Then you have an L now that varies from 0, 1, all the way to N minus 1. Okay, and the last thing in here is that ML, this number, can be anywhere 0, plus or minus 1, plus or minus 2, and all the way to L. For a choice of L, you will have this many choices for ML. It's negative. It could be negative. There is no problem with it. For the negative, that means it's a particle that is going in the opposite direction. That's all. Instead of going counterclockwise, going clockwise. That's all. In the phi direction. That's all. So these are the different conditions and the different quantum numbers. So that's the principal quantum number. This is the angular momentum, and this is the magnetic moment, magnetic quantum number. And we will see why that is when we take this thing in here and write the angular momentum in the z direction. Okay. There is one problem, and we're going to finish that one later on when we talk about the spin. Once we introduce the spin, we have the full picture for the hydrogen atom. I really did not solve the hydrogen atom problem. I just gave you a feel for it, okay? Because the math required is a little bit outside of our scope. Okay, I'm going to stop sharing. I'm just going to stop recording, and we'll pick up this discussion on Thursday. Thank you.